Hey, what's up, my chem peeps? Who's ready to take a closer look, like at the molecular level, at equilibrium? As you study this problem, it says ethene, C2H4, can be halogenated by this reaction. Boom! Where X2 can be chlorine, bromine, or iodine. Examine the three figures representing equilibrium concentrations in this reaction at the same temperature for the three different halogens. Rank the equilibrium constants for the three reactions from largest to smallest. Alright, now remember, we define our equilibrium constant, K, as the concentration of our products to the concentration of our reactants. As I look at the first box that's representing chlorine, I'm going to count up the number of my halogenated products here. I've got 1, 2, 3, 4, 5, 6, 7, 8. Do the same thing with bromine. 1, 2, 3, 4, 5, 6. And then do the same thing with iodine. 1, 2, 3, 3. Now, as I think about defining my equilibrium constant for each of these situations, I've got a large amount of product in this first example, and relatively little reactant. Let's compare that to the halogenated bromine example. We've got less product and more reactant comparative to the chlorine example. And then finally, with iodine, our K value is going to be very small, because in this example, we have very little product and quite a bit of reactant. So if I were to rank my equilibrium constant values, I'm going to go largest with the chlorine, intermediate with the bromine, and smallest with the iodine. Boom. All right, now let's take a look at a different reaction, but once again focused on a particulate representation of equilibrium. It says H2 and I2 are combined in a flask and allowed to react according to the reaction. Boom. Examine the figures, sequential in time, and we want to know two things. Which figure represents the point at which equilibrium is reached? And two, would you predict the value of K to be greater than, less than, or equal to 1? Now, you've got these images on your notes in front of you, and so I encourage you to work through this as I do it on the screen. Notice that in box 1, all I have are reactant molecules, my hydrogen in white and iodine in purple. I have no products. These images are sequential in time. As I move over to box 2, I notice that I begin to form some of my product, that HI. As I jump down to box 3, notice that I'm continuing to produce more product. So I haven't quite reached equilibrium yet. I'm continuing to make more product. Box 4, notice again that I'm making more product. I now have up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 product molecules. Let's take a look at box 5. I'm still producing more product. I'm now up to 14 product molecules. Hopefully we reach equilibrium soon because we're almost out of boxes. So look at box 6. Notice that I have the same number of product molecules that I had in box 5. My number of reactant molecules are also the same. Now, in a static image like this, it may appear like the reaction is complete. But remember, equilibrium is a dynamic process. The reaction hasn't stopped. We've just reached the point at which the rate of formation of the products equals the rate of formation of the reactants. And so those concentrations of products and reactants don't really change. And so as we look to answer this question, it's at this point in box 5 that we achieve equilibrium. And I can tell that because from this point forward, my concentrations of products and reactants don't change. The reaction keeps going, but the concentrations stay the same. Now, as I try to decide the value of my equilibrium constant K, you should recognize that we've got a lot of product, especially when we compare that to our amount of reactant. So if we're going to assign an equilibrium constant value to this reaction, I would say K is greater than 1 because we have a lot more product than we've got reactant. And we are done.